Hello students, today we are going to discuss one important topic, that is tracing of curves. Tracing of curve means finding approximate shape of the curve from the given equation. The equation would be given in any of the three forms. The first one is Cartesian curve, second one is polar curve, and third one is parametric curve. Now, as far as tracing of the curve is concerned, it is always necessary to know the approximate shape of the curve to sketch some region in the plane and find certain physical quantities like area or center of gravity, moment of inertia. So these things required to find out after getting the approximate shape of the curve. So we are having three types of the curves there: Cartesian, polar, and parametric form, and their connections. So if you take some curve here, circle in xy plane, x square plus y square is equal to a square. So if you observe this circle, all of you know what is the type of the circle it is there. This circle having center at 0, 0 and radius is a. It is something like this here. So this circle having radius a and center at 0, 0. Now polar equation for the same curve, it is there: x is equal to r cos theta, y is equal to r sin theta. So these are the polar coordinates, they are r and theta, and we express x and y in terms of r and theta by using these two equations. X square plus y square is equal to r square, then theta naturally it is tan inverse of y upon x and so on. So r is equal to a. So I put x square plus y square is equal to r square, then r square is equal to a square, means r is equal to a is the polar equation of the circle with center at 0, 0 and radius is a. Similarly, parametric equations. In parametric equations where t is parameter here, so normally it is given in terms of x and y. T is parameter. X is equal to a cos t, y is equal to a sin t are the parametric equations of this circle. So if you put x and y in this, so it is satisfied. So these are parametric equations of the circle where t is parameter over there. So take some point, the coordinates of this point, it is x a cos t, y it is a sin t. Similarly, if you take another curve here, hyperbola. This is rectangular hyperbola, xy is equal to c square. Then if you would like to have the parametric, polar equation of this curve, then we put again x is equal to r cos theta, y is equal to r sin theta over here. Then you are getting this equation. It is written as this particular form. It is r is equal to c root of something like this, sin theta cos theta. So this is also the polar equation of this hyperbola. Similarly, if you would like to write the parametric equations of the hyperbola, it is x is equal to ct, y is equal to c upon t. If you put there, then that equation must be satisfied. Similarly, you can take another conjugate hyperbolas. You can just get these three equations. So you must be able to write the equation of given curve in any of the form. That is what the first concept over here. Now, what is relation between Cartesian and polar coordinates, that I just elaborate, and then I go for tracing of the curves in each of the form Cartesian, polar and parametric. Normally in the two-dimensional coordinate system, you are having x-axis, y-axis, x dash negative x-axis and negative y-axis over there. If you take some point over here, it is pxy, then naturally everybody must know here. So if I draw perpendicular on x-axis, perpendicular on y-axis, this is origin. So this distance it is y, this distance it is x here. X means distance from y-axis, y means distance from x-axis. So you must know this thing. So this is the significance of the point pxy in xoy plane. So the location you must know. Similarly, if you would like to designate r and theta, I join O and P there. So this distance is r, this angle is theta there. So it is in this direction, theta, anti-clockwise direction. R, this is angle. This is r is this length, it is root of x square plus y square. Actually, x square plus y square. And if you take this right angle triangle there, OPM say here, then cos theta would be something, cos theta, it is x upon r, this is y here, so x upon r. Sin theta there, it is y upon r, so x is equal to r cos theta. That's what we have used right now. Y is equal to r sin theta. So this is expression of x and y in terms of r and theta. So these are relation between Cartesian and polar coordinates. Similarly, I would like to express r and theta in terms of x and y. Then naturally r would be x square plus y square, and theta would be tan inverse of y upon x for x greater than 0 and y greater than 0 in. So this is first quadrant actually, this is second quadrant, this is third quadrant, and this is fourth quadrant over here. So here in first quadrant, x positive, y positive, here x negative, y positive, and here x negative, y negative, and here a y negative and x positive. So likewise you are having, so theta is moving in this direction. So this line, so if you talk about this coordinate system, Cartesian and polar, knowing the coordinate system is very very important here. X-axis means y is equal to 0 is the equation of x-axis. Y-axis means x is equal to 0, equation of y-axis. Now r and theta, how in the polar coordinates we take theta is equal to 0 line as an initial line. Theta is equal to 0 is initial line. It is start with x-axis, theta is equal to 0. So if it is moving in this direction theta, then theta is equal to pi by 4, 45 degree. So this exactly dividing first quadrant into two parts, theta is equal to pi by 4, or it is equivalent to y is equal to x in Cartesian, and in polar theta is equal to pi by 4. Cartesian y-axis, theta is equal to pi by 2 in polar coordinates. Theta is equal to pi by 2 in polar coordinates. If you are moving likewise again, then theta is equal to pi in polar or negative x in Cartesian coordinates. Now let us come to the pole or origin. Origin means x is equal to 0, y is equal to 0. That is origin, values of x and y 0 at that particular point. So it is origin. Similarly, pole, if you are talking in polar coordinates, we take pole. So origin is pole actually. Pole means r is equal to 0. Naturally r is this thing. So naturally x 0, y 0, then r is equal to 0 is the pole. So see once again, theta is equal to 0 is initial line. Theta is equal to pi by 2 is the line passing through the pole and perpendicular to the initial line. That is what in polar coordinates, and theta is equal to pi. Now if you rotate again through pi by 2, then theta is equal to 3 pi by 2. So again theta is equal to 2 pi. So likewise theta is equal to alpha is the line always. Alpha 1, alpha 2. These are always lines. Okay. So and passing through origin naturally. And this is the way you are having structure of this coordinate system connecting Cartesian to polar or polar to Cartesian. Now we go for actual tracing of the curve in this three coordinate system. So I just go with tracing of the curve in Cartesian form. So there are two forms here in Cartesian. Y is equal to f of x generally. So y is equal to f of x means what actually? See, y is equal to f of x is explicit form actually. This is called explicit form, and this is called implicit form. What is that actually? Explicit means you can express one variable in terms of other. Explicit means you can just give the implicit means you can just give the relation between x and y. You cannot express one variable in terms of other. So in this case it is slightly complicated to judge the nature of the curve. So tracing of curve in Cartesian form. Procedure for tracing of the curve. Procedure for tracing of curve. Tracing of curve in Cartesian form. Cartesian form. Tracing of the Cartesian curve. Cartesian curve we have seen earlier, y is equal to f of x or f of x y is equal to 0. The curve given in terms of x and y. That is what the Cartesian curve. X and y are Cartesian coordinates, r and theta are polar coordinates. So curve given in terms of x and y. You know what is x, what is y. Now to find approximate shape of the curve, that is what the tracing actually, by discussing different points like symmetry, origin, tangents at origin, points of intersection, asymptote, special points on the curve, region of existence, non-existence. So these are the few points we discuss here, and finally we come to the conclusion for the approximate shape of the curve. So we start with symmetry of the given curve. So what we are going to do, here 4 points are there in the symmetry. What is there? First point, if in the equation of curve all the powers of x are even, then the curve is symmetrical about y-axis. So I just take, it is something like this, x square is equal to 4ay. All of you know it is parabola. So parabola, it is something like this, it is x square is equal to 4ay. This is parabola, this is x-axis, this is y-axis, this is origin. So all the powers of x are even, therefore the curve is symmetrical about y-axis if you observe. So it is symmetrical about y-axis. That is what the first point over here which is required to be discussed. Second point, or anything, you can take some more also, x square plus y square is equal to y square. So this curve is circle, so it is symmetrical about y-axis. Similarly, if you, second point, even powers of y, all the powers of y are even in the equation of curve, then the curve is symmetrical about x-axis. Now vice versa, if I take the equation y square is equal to 4x, then the equation would be something like this, y square is equal to 4x. This is parabola with vertex at origin, and this is the shape of this particular curve, y square is equal to 4x. And if you observe even powers of y, so the curve is symmetrical about x-axis. Similarly, if you take some more curves here, the same curve, it is continued, it is symmetrical about circle, it is symmetrical about x-axis also. And in between, suppose you are having both x and y even powers, then the curve is symmetrical about x-axis and y-axis. It is understood. Now see, interchange of x and y in the equation of curve. Whatever the equation given, if you interchange x and y in the equation of curve, that is point number 3. If you interchange x and y in the equation of curve, equation remains same. Then the curve is symmetrical about the line y is equal to x. Curve is symmetrical about the line y is equal to x. Suppose I take some curve here, say xy is equal to c square. This is rectangular hyperbola, and you know, it is something like this. So this hyperbola would be something like this. So this is the curve. So if you observe, it is symmetrical about the line y is equal to x. If you interchange x and y, the equation remains same. So it is symmetrical about the line y is equal to x. There are more curves, I can give the example. Circle also you can take it. Circle. If you interchange x and y in the equation of curve, then it remains same. So this curve is symmetrical about the line. So these are the observations you have to make there. X and y interchanged, then the curve is symmetrical about the line y is equal to x. So that is what point number 3. Now next point, it is if we put x is equal to minus x, y is equal to minus y in the equation of curve, then it remains same. Then the curve is symmetrical about opposite quadrants. Now for this, if I take the equation, say x square plus y square, this is equal to a square, the circle, again I take the circle, if I put x is equal to minus x, y is equal to minus y, equation remains same. So the curve is symmetrical about the opposite quadrants. Curve is symmetrical about opposite quadrant, it is something like this, opposite quadrant, the curve is symmetrical. Similarly, if I take for the same thing, y is equal to x cube, so this is semi-cubical parabola, it is something like this. this parabola, it would be something like this. Here is the point of inflection, and at this particular point, so if you observe, if you put y is equal to minus y, x is equal to minus x, equation remains the same. So the curve is symmetrical about the opposite quadrants. Similarly, if you take some more curves here, like ellipse also, x square upon a square plus y square upon b square is equal to 1. You know, this is ellipse, something like this, and this curve a, length of major axis, minor axis, origin. So it is symmetrical about the opposite quadrants. So many more. You can just give the example where if you replace x by minus x, y by minus y in the equation of curve, it remains same. Then the curve is symmetrical about opposite quadrants. So this is the way you have to discuss these points over there for symmetry, to trace the approximate shape or to know the approximate shape of the given curve. Second point, origin and tangents at origin. So origin, you know, well, just now we have discussed origin. What is pole? Cartesian origin, x is equal to 0, y is equal to 0. Now, if 0, 0 satisfies the equation of curve, then we say that the curve passes through origin. And further, you have to find tangents at origin. That is another important point. Tangent at origin only you have to find out if the curve passes through origin. Now, 0, 0 satisfied. Now, if you consider the circle, x square plus y square is equal to a square. If I put x 0, y 0, means 0 is equal to a square, it is not satisfied. So, the curve does not pass through origin. Now, if you observe the circle, it does not pass through origin. Now, here, it does not pass through origin. No branch of the curve passes through origin. So, we cannot find tangent at origin for this particular curve. Similarly, if I take some curve like say y square is equal to 4ax, this parabola which we have taken over here, this parabola would be something like this. Yes, this parabola. Now, if you put x is equal to 0, y is equal to 0, it is satisfied. 0 is equal to 0. Therefore, this curve passes through origin. This is origin, so it passes through origin. Now, if you observe the branch of the curve, it passes through origin. Now, next important thing here, after passing through origin, you can find tangents at origin obtained by equating lowest degree term in the equation of curve to 0. So, you have to just check out the lowest degree term. So, degree of this is 2, degree of this is 1 because 4a is constant. So, lowest degree term is 4ax is equal to 0, means x is equal to 0. X is equal to 0 means y-axis. Just now we have seen y-axis. So, this is y-axis means x is equal to 0 must be the tangent at origin. This is x-axis, this is y-axis. X is equal to 0 must be the tangent at origin. So, this is the way I just see this passes through origin, tangent at origin obtained by equating lowest degree term to 0. So, lowest degree term is 4x, x is equal to 0. X is equal to 0 means y-axis. This is tangent if you observe here. So, this is tangent at origin to this particular curve. Similarly, if you take x square is equal to 4ay, x square is equal to 4ay if you are taking, then naturally again, so this curve, so here if you observe this is tangent. So, it passes through origin. Yes, 0, 0, 0 is equal to 0. Then lowest degree term 4ay is equal to 0. 4ay is equal to 0 means y is equal to 0 is the tangent at origin. Y is equal to 0 means x-axis is the tangent at origin. Similarly, if you take some more curves here, xy is equal to c square. Rectangular hyperbola 0 is equal to c square. The curve does not pass through origin. The curve is something like this. If you try to draw it, it is this curve. So, this curve does not passes through origin. Now, I just take one unknown curve that we have not traced so far, but it is something like this. This is 3 times axy is equal to this curve. Now, if you observe this curve passes through origin, this is equal to 0. So, equating lowest degree term, 3 times AXY is the lowest degree because 3, 3, here 2. So lowest degree term equated to 0. This is called Newton's method to find tangents at origin. So xy is equal to 0. This implies x is equal to 0. There are two tangents at this particular point. So this curve would be something like this. So this curve, now we have not traced this curve. So this curve, it is there. So this curve is symmetrical about y is equal to x axis also, because if you interchange x and y in the equation of curve, the equation remains same. And here are the tangent, two tangent. This is y is x is equal to 0, and here is the tangent y is equal to 0. Two tangents at origin, x is equal to 0, y is equal to 0. These are real tangents. Origin is node at this particular point. Okay, so this is the way we can just check out the origin and tangents at origin. So ellipse also does not passes through origin. Hyperbola xy is equal to c square does not passes through origin. We go for the next point, that is point of intersection. Next point, that is third one, point of intersection with x-axis. Point of intersection with coordinate axis x and y axis, with coordinate axis, point of intersection with coordinate axis. See how it is done, point of intersection with coordinate axis, x axis and y axis. We put y is equal to 0 in the equation of curve. We get point where the curve meet x axis. Put y is equal to 0 in the equation of curve. We get point or points where the curve meet x axis. Similarly, vice versa. By putting x is equal to 0 in the equation of curve, we get point or points where the curve meet y axis. So for example, suppose I take circle x square plus y square is equal to a square. Now I put x is equal to 0. Put x is equal to 0 in the equation of curve. So what happens there? Y square is equal to a square, means y is equal to plus or minus a, means 0 a and x coordinate 0, y coordinate a, and 0 minus a are the points where the curve meet or cut x axis, y axis, because putting x is equal to 0. Similarly, if you put y is equal to 0, similarly put y is equal to 0. Similarly, put y is equal to 0 in the equation of curve. Here 0 if you are putting, then you are getting x square is equal to a square, means x is equal to plus or minus a, means x coordinate a, y coordinate 0, x coordinate minus a, y coordinate 0, and are the points where the curve meet x and y. Curve meet x axis. Means this is the way all the time. Now if you observe here, so for the circle, if you observe circle, here this point is a0, this point is minus a0, and this point is 0a, this point is 0 minus a, where the curve meet x-axis, curve meet y-axis, means circle would be something like this you are getting. So this is the way you can find the point of intersection with the coordinate axis. Now next point, for any curve, if it is meeting suppose I take x is xy is equal to c square. No curve meet x and y axis. You put x is equal to 0, you are getting 0 is equal to c square. So it is you are not getting the point of intersection. Similarly, y square is equal to 4ax. Suppose if I put x is equal to 0, you are getting y is equal to 0. If you put y is equal to 0, you are getting x is equal to 0. So for this, origin is the only point where the curve meet x and y axis. So this is the way you can just describe, you can just explain this particular points of intersection, and it is necessary to know the approximate shape of the curve by this particular point. Now next is fourth point, asymptote. Point number 4 is asymptote. Point number 4 is asymptote. There are asymptote actually is the line which meets the curve at an infinite distance. There are two types of the asymptote, parallel asymptote and oblique asymptote. There are two types of the asymptote, parallel asymptote and second is oblique asymptote. Asymptote is a straight line actually which meets the curve at an infinite distance. Now how to find out parallel asymptote? Parallel asymptote means parallel to x and y axis. It's something like this. So this is x and so this is parallel to y axis. Suppose if you consider this as y, this as x. So this is asymptote parallel to y axis. This is asymptote to parallel x axis. Oblique means it is something like this, slanted line. So this is oblique asymptote and these are parallel asymptotes. So this is parallel, this is parallel, this is oblique asymptote. So you must know the concept, you must know the straight lines or asymptote is the line which meets the curve at an infinite distance. Now how to find out parallel asymptote? Asymptote parallel to x-axis is obtained by equating coefficient of highest degree terms in x to 0, parallel to x-axis. Parallel to y-axis, again the same thing. Asymptote parallel to y-axis is obtained by equating coefficient of highest degree term in y to 0. That is what the technique of finding parallel asymptote. Suppose I take the equation, say it is y square 2a minus x. This is equal to x cube. Parallel asymptote I am talking about, and I know the shape of this particular curve would be, I know it is this is the shape, and this is the shape of this particular curve. So this is 2 times a. Now if you observe this is origin, this is y-axis, this is x-axis. Now I would like to find whether there is parallel asymptote or not. If those coefficients are not coefficients are constant, then there is no parallel asymptote to x or y axis over there. Now if I write down this as y square minus x into y square, this is equal to x cube. Now coefficient of highest degree term in x, coefficient of highest degree term in x, it is 1, which is constant, so no asymptote parallel to x axis. Now coefficient of highest degree term in y, highest degree term in y, its coefficient is this, so 2a minus x is equal to 0, it is equated to 0, so x is equal to 2 times a, is this line in fact x is equal to 2 times a, this is asymptote parallel to y-axis, asymptote parallel to y-axis. Similarly, if I consider the equation xy is equal to c square, then coefficient of highest degree term in y, x is equal to 0, coefficient of highest degree term in x, y is equal to 0. So there are two asymptotes for this particular curve, and it is something like this. So there are two asymptotes. Asymptote is the line which meets the curve at an infinite distance as x tends to infinity. So here this is y is equal to 0 asymptote and this is x is equal to 0. So this is the way you can find out asymptote parallel to x-axis and y-axis. Similarly, the technique of finding oblique asymptote. Suppose you are having some equation. Say f of xy. What is the time? time. F of xy is equal to 0.
20 minutes.
Huh?
20 minutes.
10 minutes more. Okay. F of xy is equal to 0. Procedure to find oblique asymptote for this particular curve. So asymptote is the straight line. So we consider y is equal to mx plus c is an asymptote. We assume this an asymptote. This is 2. So what we do? Substitute in this equation f of x mx plus c. This is equal to 0. This is equation 3. Now what we do here, equating coefficient of two highest degree terms in x to 0. Equating coefficients of two highest degree terms in x to 0, we get two equations in M and C. Solving those two equations for M and C, we get the values of M and C, and substituting these values over here, which was assumed here, that y is equal to mx plus c, this line to be an asymptote, we get the required straight line to be an oblique asymptote. This is the technique. There is one more technique, but this is the easy technique to find the oblique asymptote to the given curve. So this is the way you can find asymptote, parallel asymptote and oblique asymptote to the next point is region of existence and non-existence. So for the curve y is equal to f of x, if for some value of x, y square is negative, that is y is imaginary, then curve does not exist there. Similarly, if you check for this example, see, it is y square 2a minus x is equal to x cube is the curve. So we write down in this form, taking 2a minus x at the denominator. If for x greater than 2a, if you observe, if x is greater than 2 times a, y square is negative. So y is imaginary. No branch of the curve exists for x greater than 2 times a. Similarly, if x is negative, take any negative value of x, then also y square is negative. No curve exists there. So if you see the figure over here for this particular curve, this is the shape of this particular curve. X negative means this part here. If you observe, y square negative. So no branch of the curve exists, and it is marked as a cross. No curve exists there. Similarly, if x, this is asymptote to the curve, x greater than 2 times a, to the right of this line, x is equal to 2 times a, y square is negative. So no branch of the curve exists. So it is also marked as a cross line, cross. Now similarly, if you observe, between 0 and 2 times a, this point is 2 times a 0. So this is the point, this is 0, this is 2 times a. So x in between 0 to 2 times a, only the curve exists. So this is existence of the region, this is non-existence of the region of the curve, existence of the curve. So this is the way you can just check out this for region of existence and non-existence of the curve. And the last point here, it is special points on the curve, that is last one, 6th, special points on the curve. Special points on the curve. Now here what we do, for the curve y is equal to f of x, this is explicit form, we find out dy by dx at a particular point, say px1 y1, we find dy by dx for the given curve. If it is 0 at a particular point, 0, then tangent is tangent is parallel to x-axis at this particular point at px1 y1. At px1 y1, tangent is parallel to x-axis at px1 y1. Similarly, if dy by dx, if it is calculated at the same point px1 y1, that dy by dx, if it is plus or minus infinity, then tangent is parallel to y-axis at this particular point px1 y1. Tangent is parallel to y-axis at this particular point. So this is the way, these special points you have to check out the tangent parallel to x and y axis if it is 0 and plus or minus infinity. Similarly, if you are having the explicit curve, then get some values of x and y and some table and sketch those points in xy plane and just try to get the approximate shape of the curve. So these are the points. This is procedure for tracing of the curve in Cartesian form. So this is the way we are tracing the Cartesian curve x and y, starting from the symmetry, origin, tangents at origin, points of intersection, asymptote, then region of existence, non-existence, special points, and finally we are coming to the approximate shape of that particular curve. Now we trace some curves here. The first one, trace the following curves. Trace the following curves. So I take one sample curve here, following curves. I take the curve, first one, it is y square 2a minus x, this is equal to x cube. Suppose this curve I would like to trace Cartesian equations given x and y, and what would be the shape of this particular curve, that we are going to judge from the given points which we have discussed in the procedure. So the first point, it is symmetry. If you observe symmetry here, now if you observe here symmetry, all the powers of y are even, y square, it is even. So the curve is symmetrical about x-axis. The curve is symmetrical about x-axis, because all the powers of y are even, therefore curve is symmetrical about x-axis. B, origin and tangents at origin, that is our next point. Origin and tangents at origin. Origin and tangents at origin. Does it pass through origin? Just you can check by put y is equal to 0, x is equal to 0. 0, 0 satisfies the equation of curve or not. We can check out. So 0, 0 satisfies the equation of curve. Therefore, the curve passes through origin. You check out, passes through origin. And we find tangents at origin. How to find tangents at origin? By equating lowest degree term in the equation of curve to 0. To find tangents at origin, equating lowest degree, I just write down simplified form of the equation. 2ay square minus xy square, this is equal to x cube. Now lowest degree term I will consider. So this is degree 3, this is degree 3, this is degree 2 here. So lowest degree term, that is 2ay square, this is equal to 0. This implies y square is equal to 0, means y is equal to 0, y is equal to 0. Two tangents there are tangents at origin, tangents at origin. Now tangents at origin is a cusp. Cusp means coincident tangent at that particular point. It is a property of the double point. Double point means two branches of the curve passes through a point which is called double point. There are two types of the double point, one is cusp and node. Cusp means so it is something like this. So this point is a cusp. So here the tangents are coincident tangent, two tangent. In fact, this is called cusp, and node means it is something like this. Tangents are real at that particular point. So this is first tangent, this is second tangent. So this point it is called node, and this point it is called cusp. So node means real tangent at that particular point. Cusp means coincident tangent or imaginary tangent at that particular point. So origin is the cusp because two coincident tangents are there. Y is equal to 0, y is equal to 0 means x-axis. X-axis is the tangent at that particular point. So this is second point. Third point, now third point is point of intersection with x and y axis. Now put y is equal to 0, y is equal to 0, for y is equal to 0, x is equal to 0, and for x is equal to 0, y is equal to 0. So origin 0, 0 is the only point, is the point where the curve meet curve meet x and y axis, x and y axis. So origin is the only point where the curve intersect x and y axis. Now next point I go here, that is D. It is asymptote to this curve. D is asymptote if any, may be, may not be, y square 2a minus x is equal to x cube, 2a minus x cube. Now what we do to find out the first parallel asymptote? If it is parallel asymptote, no oblique asymptote. So you have to check out coefficient of highest degree term, y square, highest degree term in x, it is, its coefficient is 1. So no asymptote parallel to x axis, asymptote parallel to x axis, no asymptote parallel to x axis, asymptote parallel to y axis, equating coefficient of highest degree term in y, coefficient of highest degree term in y is 2a minus x is equal to 0, or this implies x is equal to 2 times a, x is equal to 2 times a is asymptote parallel to y axis, asymptote parallel to y axis, and no oblique asymptote. Next is approximate shape of this particular curve, or region of existence or non-existence, region of existence and non-existence. So we write down this y square is equal to x cube upon 2a minus x. So if you observe region of existence and non-existence, for x less than 0, negative, x negative, y square is negative, so y is imaginary, and for x greater than 2 times a, y square is negative, y is imaginary. So for x negative and x greater than 2 times a, the curve does not exist. Or no branch of the curve branch of the curve, no branch of the curve exists. Curve exists. So curve exists only for 0 is less than x is less than 2 times a. If x less than 2 times a and for x greater than 0, the curve exists. So this is the way you are having all these points discussed, and approximate shape of the curve is as shown in the figure. Approximate shape of the curve is as shown in the figure. So that we draw here. The shape of the curve is something like this. So here is the tangent. This is the point 2 times a0 by putting x is equal to 0. Y square, point of intersection, y square 2a minus x. This is equal to x cube. So 2 times a0 is this particular point. This is asymptote to this curve. Asymptote, x is equal to 2 times a, x-axis, y-axis, this is origin, x dash, y to y dash, and you have to take the judgment of this particular curve. Here the curve does not exist. This is the region for x greater than 2 times a. This is the region for x negative. Here the curve does not exist, and you can have this particular curve x cube in the explicit form 2a minus x. If I put y is equal to x is equal to a, then what happens? See, you are getting y square. This is equal to a cube upon 2a minus a. So this is equal to, it is a square. Y square is equal to a square. So y is equal to plus or minus a. So these are the points on the curve a and a minus a. So this point is located over here. It is a is somewhere here and one point here. So means you are getting, this is asymptote, and here is the branch of this particular curve. It would be something like this. So this is the point, this is P point, this is Q point, this is point P, this is point Q, this is A, and this is A minus A over here. So this is approximate, and this is cusp, which we have seen already. Y is equal to 0, y is equal to 0. This point is cusp for this particular curve, and this is asymptote. X is equal to 2 times a, and this is shape of this particular curve. So this is the way you can trace out this curve. This is second curve. We are going to trace in Cartesian form. The second curve is x cube plus y cube is equal to 3 times axy, where a is some constant which is greater than 0. This curve is known as Fullium of Descartes. Now, according to the procedure, we are going, if you observe in the equation of curve, if we interchange x and y in the equation of curve, it remains same. So it is symmetrical about the line y is equal to x. This is first point. Second, 0, 0. If you put x is equal to 0, y is equal to 0, 0 plus 0, this is equal to 0. It satisfies the equation of curve. So curve passes through origin. Then if it is passes through origin, equating lowest degree term, we find tangents at origin by equating lowest degree terms to 0. So lowest degree term, here degree is 3, and here degree is 2. So this is lowest degree term in the equation of curve, that is on the right hand side. So I equate it to 0. 3a xy is equal to 0. 3a is not equal to 0. Xy is equal to 0. So x is equal to 0. Y is equal to 0 are tangents at origin. X is equal to 0 means y axis. Y is equal to 0 means x axis are the tangents at origin. The next is minus x minus y. That is the third quadrant. does not satisfy. If you observe, if you put here the equation of curve, so no part of the curve, no branch of the curve located in third quadrant. Now points of intersection with x and y axis. It's obviously, if you put y is equal to 0 in the equation of curve, you are getting x is equal to 0, and if you put x is equal to 0 in the equation of curve, you are getting y is equal to 0. So 0, 0 is the only point where the curve meet x and y axis. Now point of intersection with the line y is equal to x where the symmetry occurs. So y is equal to x, if you are putting in the equation of curve, you are getting this, then this thing, y is equal to x or x is equal to y, you are putting. So y is equal to x, if you are putting, then you are getting 2 times x cube, 3x square. Then this thing, this term taken on that side, so x square, it is taken common. So either x is equal to 0 or x square is equal to 0. 2x is equal to 3 times a means x is equal to 3a by 2. So for x is equal to 0, y is equal to 0 in the equation of curve, and if you put x is equal to 3a by 2, y is equal to 3a by 2. Means 0, 0 and 3a by 2, 3a by 2 are the points where the curve intersect the line y is equal to x. The line y is equal to x means origin and the point which is located in first quadrant. Now next is finding asymptote for this curve. Asymptote for this particular curve, we find out whether it is parallel or oblique asymptote, that we shall see. So x cube plus y cube is equal to 3 times axy is the curve. Asymptote parallel to y axis. How it is obtained? By equating coefficient of highest degree term in y, that is y cube, and its coefficient is 1, so no asymptote. 1 is constant, so no asymptote parallel to y axis. Similarly, to find asymptote parallel to x axis, coefficient of highest degree term in x, that is 1, so we cannot equate it to 0, so no asymptote parallel to x axis. Now we go for the oblique asymptote. To find oblique asymptote for this curve, x cube plus y cube, this is equal to 3 times axy. So according to the procedure, we consider the line, or let y is equal to mx plus c and be an oblique asymptote to this curve. So you are putting y is equal to mx plus c in the equation of curve, be an oblique asymptote here, oblique asymptote, be an oblique asymptote. So you are putting here plus mx plus c bracket cube, this is equal to 3 times ax, y is replaced by mx plus c, and we simplify this and we equate coefficients of to highest powers of x to 0. So x cube plus, now I just open this by a plus b bracket cube, so it is m cube x cube plus c cube plus 3 times mx c square plus 3 times m square x square into c, and this is equal to right hand side 3 times am x square plus 3 times acx, 3 times acx. Now we just rearrange the terms here. So the terms are 1 plus m cube into x cube plus terms of x square, this term is there, this term, rest term can be resected here, 3 times m square c minus 3 times am x square, taking this term on the right hand side, and so on. This is equal to 0. So remaining term x need not be considered. So two highest degree terms in x. So two highest, x cube and x square. So here it is 1 plus m cube is equal to 0, and next is 3m square c minus 3 times am is equal to 0. So it has the real root is only m is equal to minus 1, rest are imaginary roots there. So I divide this by 3 there. So m square c minus am is equal to 0, or this implies you are getting this as dividing by 3m in fact. So this m also gets cancelled. So you are getting this as c mc is equal to a. So c is equal to m is minus 1, so c is equal to minus a. Over here you are getting the values, and m is equal to minus 1. So these values we are putting in this particular equation. So y is equal to m is equal to minus 1, and c is equal to minus a. So you are getting this as c is equal to minus a. So you are getting x plus y is equal to minus a, or x plus y plus a is equal to 0 is the required oblique asymptote for this particular curve. So this line is the oblique asymptote, x plus y plus a is equal to 0. So we proceed for some special point on the curve. So we have seen now next is x cube plus y cube. This is equal to 3 times axy. We just check out the tangent at a particular point, origin, it is already obtained. Then at this particular point, 3a by 2. So we find out tangent at this particular point. So the tangent dy by dx, if you try to find out for this dy by dx, we find out tangent. For tangent, you need to find dy by dx. So we differentiate this 3x square plus 3y square dy by dx, and this is equal to 3 times a x into dy by dx plus 3 times a into y. You can cancel out 3 throughout from here. So you are getting dy by dx to be, so collecting the terms of dy by dx, y square dy by dx I just take this term on the right hand side, minus ax dy by dx, collecting the terms of dy by dx, and the right hand side would be something ay minus x square. So dy by dx, you are getting this as dy by dx is equal to ay minus x square divided by y square minus ax. So we find out dy by dx at this particular point, dy by dx at this particular point p, say it is 3a by 2. So if you observe this, if you work out this, then you are getting something like this. If you simplify this, y is 3a by 2 minus x square, it is 9a square divided by 4 divided by y square, it is again 9a square divided by 4 minus a into x, it is 3a by 2. So if you simplify this, you are getting this is minus 1. So dy by dx at this particular point, it is minus 1. So tangent at this particular point, it is perpendicular to the line y is equal to x, because slope of this is 1 actually, and slope of this is minus 1. So tangent at this particular point, it is perpendicular to the line y is equal to x. Now we come to the approximate shape of this particular curve, and that shape would be something like this here, Fulham of Descartes. The shape, it is in the XOY plane, x-axis, this is y-axis, this is line, y is equal to x over here, then asymptote is x plus y is equal to a plus a is equal to 0. For y is equal to 0, x is equal to minus a. For x is equal to 0, then y is equal to minus a. So the points are minus a0 may be where here minus a0, and next point it is 0 minus a. So the line passing through this, that is this line, and this line is x plus y plus a is equal to 0. This is asymptote. Now the point of intersection, this line y is equal to x. Point of intersection with the line and the curve, it is origin 0 0 and 3a by 2, 3a by 2. At this particular point, tangent is perpendicular, means to the curve. This is tangent, so naturally, and origin also we are having the tangent, x is equal to 0, y is equal to 0. So, and here is the loop formation, this particular point. So this is your line. If you try to find out, this line would be, if you try to find out, there is x is equal to 3 times a is the line, and this is y is equal to 0, this is x is equal to 0. So this is origin, two tangents, real and distinct tangent. So this point is called cusp. This point is called cusp. So this is the approximate shape of this particular curve. This is called Fulham of Descartes. It is standard curve. Now we go for another curve here quickly, curve number 3 in the Cartesian form, and that curve is, it is something like this. Trace the curve root x plus root y, this is equal to root a. Now we go with the procedure. Point number 1, symmetry. Now if you observe, no powers of x, no powers of y are even, or so no symmetry about x and y axis over there. Now if you interchange x and y in the equation of curve, it remains same. So the curve again symmetrical about the line, y is equal to x. If you interchange x and y in the equation of curve, it is symmetrical about the line, symmetry about the line, y is equal to x. Because if we interchange x and y in the equation of curve, it remains same. Second, origin and tangents at origin. Now if you observe, put x is equal to 0, y is equal to 0, 0 is equal to root a, so it is not equal, it is not satisfied. So the curve does not pass through origin, curve does not pass through origin, does not pass through origin, curve does not pass through origin, so no tangents at origin, no tangents at origin. Then next is third one, points of intersection with x and y axis. Now put y is equal to 0, put y is equal to 0. If you put here root x is equal to root a, root x is equal to root a, means you are getting x is equal to a there. And similarly, if you put x is equal to 0 in the equation of curve, naturally you are getting y is equal to a. So a0 and 0a are the points of intersection of the curve with x and y axis respectively, are the points of intersection, points of intersection with x and y axis respectively, Now fourth point is, we find out the point of intersection with the line, because it is symmetrical about the line. So put y is equal to x in the equation of curve, put y is equal to x to get the point of intersection with the line y is equal to x. So I put it here, y is equal to x, root x, this is equal to root a. So 2 times root x is equal to root a. So root x is equal to, it is root of a divided by 2 means x is equal to a by 4. Similarly, therefore, y also equals to a by 4 because y is equal to x. So, a by 4 are the points of, or is the point of intersection, of line y is equal to x with the curve. Now we find dy by dx special point or tangent at some particular point, or no asymptote for this curve because it is explicit. So no parallel asymptote if you observe. So coefficient of highest power of x, coefficient of highest power of a y, that is constant. So no parallel asymptote, no oblique asymptote. Now we find tangent at special point, tangent at a0 and 0a, tangent at a0 and 0a for this particular curve. So for the curve root x plus root y, this is equal to root a. We have to find tangent. So for that we find dy by dx. So find dy by dx for this. So differentiating with respect to x. So root x derivative is 1 upon 2 times root x. Derivative of root y is 1 upon 2 times root y into dy by dx. This is equal to constant. Its differentiation is 0. So these two may be getting cancelled from here. So 1 upon root y dy by dx. This is equal to minus 1 upon root x. So dy by dx you are getting, this is equal to minus root y upon root x. Root y upon root x. Now we find out tangent at a particular point a0 and 0a. At a0 dy by dx at a0, where the point of intersection with x-axis a0. So if I put x is equal to a, y is equal to 0, so you are getting 0 upon root a. So this is equal to 0. So tangent is parallel. Tangent is parallel to x-axis at a0. Similarly, if you try to find dy by dx at a particular point, similarly dy by dx, if you try to find at the point 0a, then you are getting similarly dy by dx at 0a. If you try to find, it is minus, then it is root a divided by 0, it is minus infinity. So tangent is parallel to y-axis at the point at 0a. So this is the way we are having tangent at these special points with the point of intersection with x and y-axis. So, and the approximate shape of this particular curve is this. So approximate shape of the curve is something like this. Now if you observe, you can just trace the curve. This is origin, this is y-axis, and this is the line y is equal to x, where the curve is symmetrical about, and you are having this point here is the tangent for this curve. Tangent at this particular point is 0a. This point is a0, this point, and at this particular point here, this point is a by 4, and point of intersection with this. So here is the tangent, and this is approximate shape of this particular curve, which is symmetrical about the line y is equal to x. So this is the procedure for, this is the way you can trace this Cartesian curve given in x and okay. The last curve, trace the curve x square plus y square, a x square minus y square, a greater than 0. Now this is Cartesian curve in terms of x and y. So we go with the procedure. All the powers of y, if you observe, are even in the equation of curve. So symmetry about x-axis naturally. So here if you observe, so this is simplified form. All the powers of y are even. So the curve is symmetrical about x-axis. Now next is 0, 0. If you put x is equal to 0, y is equal to 0 in the equation of curve, it satisfies. 0 is equal to 0 satisfies the equation of curve. Satisfies means LS is equal to RHS. Passes, therefore curve passes through origin. If the curve passes through origin, then only we find tangents at origin by Newton's method. That method is to find tangents at origin, equating lowest degree term to 0. So this is simplified form, and lowest degree term is ax square minus y square. Here degree is 3, here degree is 3, here 2, 2. So it is equated to 0. So you are getting y is equal to plus or minus x. Two tangents, y is equal to x, y is equal to minus x are two tangents at origin. So this is completion of point number 2. Now next is third point. It is point of intersection with x and y axis. So how it is obtained? Point of intersection with x and y axis. So if you put y is equal to 0 in the equation of curve, see what is happening. If you put y is equal to 0 in the equation of curve, then you are getting put y is equal to 0. That is third point. Put y is equal to 0 in the equation of curve. So you are getting something x cube. This is equal to, if you put y is equal to 0, a x square. So you are getting x cube minus a x square is equal to 0. This implies x square taken common, x minus a is equal to 0. So this implies x is equal to 0, x is equal to a. So if you put y is equal to 0, you are getting x is equal to 0. For x is equal to 0, if you check out, y is equal to 0, and for x is equal to a, y is equal to 0. So what happens here? 0, 0 and a 0 are the points where the curve meet x-axis, where the curve meet x-axis, where the curve meet x-axis. Next is fourth one, asymptote. So we can write down here the explicit equation of the curve, x cube plus it is xy square. This is equal to a x square minus ay square. This simplified form. So I can write down this as xy square plus ay square. This is equal to ax square. Ax square, I call this is equation 1, ax square minus x cube. I take common y square here, so it is x plus a. This is equal to ax square, or I just take x square common inside the bracket, a minus x. So y square is equal to x square a minus x divided by a plus x or x plus a. So this is the simplified form, explicit form, where it is necessary, it is easy to analyze the equation of the curve for tracing. Now what I do, the next particular point here, if you for the asymptote, now if you observe asymptote, coefficient of highest degree term in y, highest degree term in x. Now highest degree term in y, x, it is this. So 1. So no asymptote, coefficient of highest degree term in x cube, its coefficient 1. So no asymptote parallel to x axis. Similarly y axis, so highest degree term in y, this term, and this term I will collect. So I just take into consideration xy square plus ay square to check the asymptote. So x plus a into y square. So this is equal to this coefficient of highest degree term in y. This is the coefficient. So x plus a is equal to 0 or x is equal to minus a is the asymptote parallel to y-axis. Coefficient of highest degree term in y to 0. So x is equal to minus a is the asymptote parallel to y-axis. No oblique asymptote for this particular curve. Now next we find out dy by dx for this. Dy by dx. We find dy by dx for this particular curve. X cube plus xy square. This is equal to a x square minus y square. Now we find out dy by dx, and dy by dx at this particular point, if you try to find out this dy by dx at a0, you just work out this would be plus or minus infinity. You are getting there, plus infinity or minus infinity. So tangent is parallel to y-axis at this particular point. Tangent is parallel to y-axis at this particular point. And now region of existence and non-existence. Region of existence and non-existence. Region of existence and non-existence. So y square is equal to x. Y square is equal to x square into x minus a divided by x plus a. Now if you observe here this curve, so this is the explicit form of the equation. If you observe this equation for x greater than a, x should be, a minus x here, x should be less than this. So this is simplified form. Now if x greater than a, y square becomes negative. Y square is negative. So no curve exists for x greater than a. Similarly for x less than minus a, from here y square is negative. Similarly for x negative also, the curve does not exist. X negative, same thing, y square is negative. So no curve exists for these boundaries here, x greater than a, x less than minus a, and x less than 0. And approximate shape of this particular curve is something like this from the given information or whatever the point we have discussed over here. It is this curve. Now if you observe x-axis, this is y-axis, this is asymptote to this curve. X is equal to this point is minus a 0, x is equal to minus a, this is asymptote for this curve. Now here are the tangents. If you observe, y is equal to minus x, this is y is equal to minus x, this tangent is y is equal to x, y is equal to x, and here is the tangent at this particular point a0. Here is also tangent, because dy by dx is equal to infinity at this particular point. If you check out this is x is equal to a, and here are the tangents at origin. Now if you observe, this is asymptote, so the branch going like this, and here is the loop formation. So it is something like this. So this is approximate shape of this particular curve. So length of this loop is A. This is y is equal to x tangent, y is equal to minus x tangent, and this is asymptote, x is equal to minus a, and this is origin, and tangents at this particular point are real tangent, distinct tangent, so origin is a cusp. So this is approximate shape of this particular curve. Okay, so this is tracing of curve in Cartesian form. Now we go for polar curve now, procedure for tracing of polar. So next curve is polar curve that we are going to trace, and there is procedure for tracing of the polar curve. R is equal to f of theta, or in the implicit form f of r theta is equal to 0. Now I just introduce polar coordinates first. Already it is introduced, but just quick revision. So this is the figure. R and theta are the polar coordinates, r length of the radius vector as shown in the figure. Theta is the angle made by the line OP with x-axis or the initial line. Theta is equal to 0. Now if you observe the figure, initial line theta is equal to 0, theta is equal to pi by 2, r is the length, theta is angle made by this OP with the initial line. Then theta is equal to pi, this is pi by 2, again pi by 2, theta is equal to pi, r is equal to 0 is the pole actually, so this is pole, r is equal to 0 is the pole, then theta is equal to 3 pi by 2, again rotating through pi by 2, and again to the initial position, theta is equal to 2 pi, means theta is equal to 0, that is what the polar plane. Now procedure for tracing of this particular curve, r is equal to f of theta. We start with the symmetry as usual to Cartesian form. So if you put theta is equal to minus theta in the equation of curve, it remains the same. Then the curve is symmetrical about initial line. Means half part is located above, half part located below. That is what the symmetry about initial line, theta is equal to 0. Similarly, if we put r is equal to minus r in the equation of curve, then equation remains the same or unchanged. Then the curve is symmetrical about the pole. Pole means it is r is equal to 0, means the curve is symmetrical about pole. Similarly, third point of the symmetry, if we put r is equal to minus r, theta is equal to minus theta in the equation of curve, then the curve remains same or the equation remains same, then the curve is symmetrical about theta is equal to pi by 2. Theta is equal to pi by 2, in fact the line passing through the pole and perpendicular to the initial line, or in Cartesian it is y-axis. So the curve is symmetrical about this, means half part located on this side, half part located on this side. So that is what the first point, it is symmetry. Now next point, it is pole and tangents at pole. Pole and tangents at pole, that is B. B point, it is pole and tangents at pole. Now what is happening here? Pole, as I said right now, for some value of theta, r becomes 0, r becomes 0, then curve passes through pole, or pole lies on the curve, Now as usual, if curve passes through pole or pole lies on the curve, to find equation of tangent at pole, equation of tangent at pole, put r is equal to 0 in the equation of curve. So suppose I consider the equation, say r is equal to a 1 plus cos theta. Now if you observe this particular curve, for theta is equal to pi, if you observe cos pi is 0, cos pi is minus 1, minus 1 plus 1, so r is equal to 0. Means curve passes through pole. And to find tangent at pole, put r is equal to 0. So what happens here? If you put r is equal to 0, then a 1 plus cos theta is equal to 0, and this implies 1 plus cos theta is equal to 0, or this implies cos theta is equal to minus 1, means theta is equal to plus or minus pi are the tangents at pole. So you can find out tangent at this particular point, or tangent at origin, or tangent at pole. So this is the second point. Similarly, the next point is of the procedure is C. It is next point, preparing table for values of r and theta. So theta is the angle, r is the length of the radius vector. So you have to prepare table for the values of r and theta. It is somewhat, you take the suitable values of r and theta. So this is r, this is theta. So you have to put the values of angles and corresponding, you have to find out r. So like this, and after preparing table for the values of r and theta, you have to find the value of theta for which r is maximum, and find the value of theta for which r is minimum, and observe how r varies with respect to theta, and locate this point in polar plane, and accordingly you can get the approximate shape of that particular curve. Now next point, it is angle between radius vector and tangent. Angle between radius vector and tangent. So it is obtained by the formula tan phi. Phi is actually angle r d theta by dr. It is obtained by this particular formula. Now if you observe this, suppose this is the curve, this is radius vector, and this is tangent. So this is psi, this angle is theta, this is r, this is PR theta, and this is equation of the curve r is equal to f of theta, which we are tracing. This is pole, this is theta is equal to 0, this is theta is equal to pi by 2, and this angle is actually angle phi, and it is required to find out by the formula tan phi is equal to r d theta by dr. Now why to find out this angle? So this is the curve, so we will come to know what is the direction of tangent at this particular point, at some particular point p r theta. So psi, naturally it is theta plus phi. psi is equal to theta plus phi, and this angle is angle between radius vector and the tangent. Psi is equal to theta plus phi, and it will indicate the direction of tangent at a particular point for the curve. And finally, the region of existence and non-existence, that is the last point, region of existence, non-existence for the curve r is equal to f of theta. It is E point, r is equal to f of theta, existence and non-existence in fact. So it's very clear, for some value of theta, if r square is negative, means r is imaginary, no part of the curve exists there. So you have to determine the value of theta normally, and this is the region of existence, and you have to determine, confine the values of theta for which the r exists there. So this is region of existence, and finally you need to have the approximate shape of the curve by discussing all these, taking into consideration from A to E, and get the approximate shape of the curve. So this is actually the procedure for tracing of the Cartesian, polar curve. Now we just take one curve, trace the curve, trace the curve, trace the curve, say r is equal to a 1 plus cos theta. R is equal to a 1 plus cos theta. This is actually a standard curve. This is called caridoid. This is heart-shaped curve. So it is caridoid. There are 3 more caridoids of different shapes. So this is caridoid. Now we go with the procedure for tracing of this particular curve. Now procedure, first point, it is symmetry. First point, it is symmetry. So symmetry. Now if you observe, there are 3 points in the symmetry. If we put theta is equal to minus theta, theta is equal to minus theta in the equation of curve, r is equal to a 1 plus cos minus theta. So equation remains same. So r is equal to a 1 plus cos theta. So the curve is symmetrical about initial line theta is equal to 0. Initial line theta is equal to 0. That's all. B. Next is, now for which value of this equation, if you observe, for this curve r becomes 0. If you observe here, for theta is equal to pi, for theta is equal to pi, r is equal to a 1 plus cos pi, or this is equal to a 1 cos pi is minus 1, so it is 0, r is equal to 0. So the curve, so we are able to find value of theta for which, for theta is equal to pi, for which r is equal to 0. Therefore the curve passes through pole. Curve passes through pole, or pole lies on the curve, Now to find tangent at pole, as usual, to find tangent at pole, we put r is equal to 0. To find tangent or tangents at pole, put r is equal to 0 in the equation of curve. So what happens here? So if I put r is equal to 0, then a1 plus cos theta, this implies a is not equal to 0, so 1 plus cos theta is equal to 0, so cos theta is equal to minus 1, so theta is equal to, for which value it is minus 1, plus or minus, by r tangents at pole, tangents at pole, or tangents at pole. So these are tangents at pole, and here it is symmetrical about this, and for theta is equal to pi, r is equal to 0. So the next point, we prepare table for the values of r and theta. So the next point, it is table for the values of r and theta. Now if you observe, r is equal to a 1 plus cos theta for theta and r. So for theta, I take some suitable values here, few values. For theta is equal to 0. So if you observe, theta is equal to 0, cos 0 is 1, 1 plus 1 is 2, means this value is 2 times a. For theta is equal to, you can take say pi by 2 or pi by say 3, means 60 degree. If you are taking, then cos 60, it is half. So you are getting this value 3a by 2, cos pi by 2, cos pi by 2 is 0. So 0 plus 1 is 1, so you are getting this value, it is a. And for theta is equal to, you can take in between value or pi also. If it is pi, then r becomes 0 here. Then next value is say 3 pi by 2, then 3 pi by 2, cos 3 pi by 2 is 0, then r is equal to a, then r is equal to 2 pi, then cos 2 pi is 1, so it is 2 times a, and so on. So I just take the, you can take in between pi by 6 also, pi by 4 also, these values, and look at these points there. So this is table for the values of r and theta. So, and you have to observe how r varies with respect to theta, and you have to determine the value of theta for which r is maximum and r is minimum. So let us see how to locate the first point. It is r 2 times a, first point 2 times a 0, second point it is 3a by 2 pi by 3, third point it is a pi by 2, next point it is 0 pi, next point it is a 3 pi by 2, and so on. We just try to locate these points there. Now if you observe, as theta increases from 0 to pi, theta increases from 0 to pi, r decreases, length of the radius vector decreases from 2 times a to 0. Theta angle increases from 0 to pi, means 180 degree. R decreases from 2 times a. Similarly, 2 times a to 0. Now theta increases from pi to 2 times pi. R increases from 0 to 2 times a. That is length of the radius vector increases from 0 to 2 times a. Now if you observe the maximum value, again you can take the next cycle. So maximum value of r, it is 2 times a, and minimum value of r is 0. So we look at this in the plane. It is this is approximate shape of the curve. So we just try to locate this. This is theta is equal to 0. This is theta is equal to pi by 2. This is theta is equal to pi, and this is theta is equal to 3 pi by 2. So if you observe, now we try to locate these points in the plane. 2 times a 0 means length of this is r, it is 2 times a, and theta is equal to 0. Theta is equal to 0. So I just take the length, it is 2 times a, and here is the point 2 times a 0. Here is the point 2 times a 0. Second point, it is 3a by 2 pi by 3. 3a by 2 pi by 3. So this point is most probably pi by 3 means 60 degree. Somewhere here it is 60 degree with somewhere here, and length is 3 by 2 means 1.5a, So this is your next point, 3a by 2, pi by 3. This is second point, this is first point, and this is the length. This angle is pi by 3, 60 degree. This angle is 0. The next is a, it is pi by 2. So this is next point, a pi by 2. This is next point. So a would be exactly here. It is half than this. So it would be something like this. It is a, and next point 0 to pi, r becomes 0. That is the next point. R is equal to 0 for theta is equal to pi. So this is next point. Again, it is increasing. It is decreasing here. R increasing from theta is equal to pi to 3 pi by 2. If you observe from 0 to a. So here again, this point it is a, and again it is increasing up to 2 times a. So this point. So accordingly, you are having this approximate shape of this particular curve would be something like this. So it becomes 0 again, and again increases. It is again a, and it becomes 2 times a. So this is the way you are having this approximate shape of this particular curve. R is equal to 0, theta is equal to pi, this length a, theta is equal to 0, pi by 2, pi, and this is called caridoid. This is heart shaped curve, this is caridoid. So this is, now at this particular point you have to find the tangent, 2 times a0. So how to find tangent? That is by angle between radius vector and the tangent. How to work out that? D, angle between radius vector and the tangent, by the formula tan phi is equal to r d theta by dr. So r is equal to a 1 plus cos theta. So dr by d theta I will find out. It is derivative minus a sin theta. So I put the value here. Therefore tan phi is equal to, I put the value here, this is equal to r. R is actually, it is a1 plus cos theta from the equation of curve divided by minus a sin theta dr by d theta. It is just a reciprocal of this. So a gets cancelled, 2 times cos square theta by 2 divided by, this gets cancelled, minus 2 times sin theta by 2 cos theta by 2 by half angle. So this gets cancelled. You are getting minus, this cos also gets cancelled, minus cot theta by 2. Cot theta by 2. This is for tan phi. This is for tan phi. I put it in terms of tan. So tan of pi by 2 plus theta by 2. So you are getting phi angle as pi by 2 plus theta by 2. But if you observe, so we need this phi at theta is equal to 0. At theta is equal to 0, phi is equal to pi by 2 is nothing but psi actually. So tangent, psi means actually the tangent is this, psi is equal to pi by 2, which is perpendicular to the initial line, theta is equal to 0, because psi is equal to, actually psi is equal to theta plus phi. Theta is 0, so psi is always equals to phi there, because it is at this particular point where theta is equal to 0. So this is the way you are having this approximate shape of this particular curve. Now similarly you are having other caridoids also. So you can just trace by the similar way other caridoids. R is equal to the second caridoid. Second caridoid, it is R is equal to a 1 plus cos theta, 1 minus cos theta. Now 1 minus cos theta, naturally for theta is equal to 0, if you observe theta is equal to 0, 1 means R is equal to 0. Cos 0 is 1, 1 minus 1 is 0. Theta is equal to pi by 2. Cos pi by 2 is 0 means R is equal to a. Theta is equal to pi. So R is equal to 2 times a. theta is equal to 3 pi by 2, 3 pi by 2, 3 pi by 2, r is equal to a, and theta is equal to 2 pi, 2 pi, it is 0, so r is equal to 0, because cos 2 pi is 1, 1 minus 1 is 0. So shape of this particular curve would be something, you can look at the point 0, 0, theta is equal to 0 means this is first point, this is second point, so it would be something like this. So if you trace this, it would be something, this is a, this is theta is equal to, this is 2 times a, because this is pi, theta is equal to pi, r is equal to 2 times a, this is theta is equal to 0, theta is equal to 0, and something like this one r is equal to 0. Similarly, you can have the other choroids, r is equal to a 2 times a, this is theta is equal to pi by 2. Similarly, r is equal to a, okay, I will take it, 5 minutes are there.
4 minutes.
Okay, r is equal to a 1 plus sine theta. Similarly, 1 plus a sine theta means naturally for theta is equal to 0, r is equal to sine 0 is 0, a, theta is equal to pi by 2, r is equal to 2 times a, then theta is equal to pi, r is equal to a, because sine pi is 0, theta is equal to 2 pi or 3 pi by 2, 3 pi by 2, r is equal to 3 pi by 2 means minus 1, so you are getting 0, for theta is equal to 2 pi, r is equal to 2 pi, it is 0, r is equal to a. So somewhat like this, theta is equal to pi, it is theta is equal to 3 pi by 2, it is minus 1. So somewhat like this, and shape of this particular curve would be something like this. Theta is equal to 0, r is equal to a is the first point. Theta is equal to pi by 2, r is equal to 2 times a. This length is a, this length is 2 times a, and theta is equal to pi. Again, r is equal to a. So this is another point here, and theta is equal to 3 pi by 2, r is equal to again 0. So at this particular point, so it would be this point, and for 2 pi again it is a. So this one, it is somewhat like this. So it would be somewhat like this, and here this is the way r increases, decreases, and this length is 2 times a. This theta is pi by 2, for theta is equal to 0, for theta is equal to pi, and theta is equal to 3 pi by 2, and here is the pole, r is equal to 0. Now similarly you can have the curve fourth one, r is equal to a 1 minus sine theta. It would be naturally, if you take the limits and just work out, it would be something like this. If you just take inverted to this particular form, a, this is pole, this is theta is equal to pi by 2, this is theta is equal to pi, I'm sorry, 0, this is theta is equal to pi, this is theta is equal to 3 pi by 2. If you observe, it is 2 times a, theta is equal to 3 pi by 2, because 3 pi minus plus 2 times a over here, this is 2 times a, and this is these are the points you are having, and this is the shape. So this is shape of this all these choroids. These are important curve as far as the polar curve are concerned. Hello students. In the earlier videos, we have seen choroids, four choroids. Now fifth one is r square is equal to a square cos 2 times theta. This is polar curve in terms of the coordinates r and theta. This is also called a Laminscate of Bernoulli or Bernoulli's Laminscate. This is standard curve. So to trace this polar curve, we go with the procedure. So the step number 1 is symmetry. Now if we put theta is equal to minus theta in the equation of curve, that is cos minus theta is cos theta. So equation remains same. Therefore the curve is symmetrical about the initial line theta is equal to 0, and it is symmetrical about theta is equal to pi by 2 also, because if we put r is equal to minus r, theta is equal to minus theta in the equation of curve, it remains same, because minus r bracket square cos minus theta is cos theta. So this is about symmetry. Now the next point is pole and tangents at pole. Whether the curve passes through pole or not, that we have to check out. So for theta is equal to pi by 4 is the value for which r becomes 0, if you observe. So pi by 4 I have put in the equation of curve. So a square cos pi by 2, cos pi by 2 is 0, that's why r square 0 means r is equal to 0. So the curve passes through pole or pole lies on the curve. Now to find tangents at pole, we put r is equal to 0 in the equation of curve. So r is equal to 0 I have put in the equation of curve. Cos 2 theta is equal to 0 because a square is not equal to 0. So 2 theta is equal to, you are getting the multiple values, minus pi by 2, plus pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, for which this cos of the angle is 0. Now further I take this 2 on this side, so simplification, these are tangents at pole, minus pi by 4, plus pi by 4, 3 pi by 4, 5 pi by 4 and so on, these are tangents at pole. Now we prepare a table for the values of r and theta. So we take some suitable value and check out r here. For theta is equal to 0, if you observe, theta is equal to 0, r square is equal to a square, means r is equal to a plus or minus a. Similarly, theta is equal to pi by 4, if we put, r becomes 0 there, for theta is equal to pi by 4. Similarly, theta is equal to pi by 2, if you try to put, cos pi is minus 1, so r square is equal to minus 1, minus a square. R square is equal to minus a square means r square negative, so curve does not exist. If you take some other values also, here say pi by 3, then also r square, similarly some more values, pi by 6, then r becomes, theta is equal to pi by 3, r becomes negative. Similarly, some values here also you can take, it becomes negative. So from pi by 4 to 3 pi by 4 means pi by 4 to 3 pi by 4, r square negative, and curve does not exist over here. Similarly, for theta is equal to pi, pi by 4 it becomes 0, theta is equal to pi, r is equal to minus a, if you observe, theta is equal to r square is equal to minus a, that is radius vector negative, 5 pi by 4, if you take the value it becomes 0, 3 pi by 2 again infinity, again 7 pi by 4 it is 0. So from here to here, 5 pi by 4, if you observe the figure, 5 pi by 4 to 7 pi by 4. So here r square negative, so curve does not exist, r is imaginary, so curve does not exist over here. Similarly, 2 pi if it becomes, it is merging with theta is equal to 0, r again becomes a over here. Similarly, to find angle between radius vector and tangent, by the formula tan phi is equal to r d theta by dr. To try to find out this angle by the formula, you are getting phi is equal to pi by 2, that is tangent is perpendicular to the initial line at this particular point and at this particular point minus a0. If you try to find out tangent at this particular point after differentiating and putting the values, you are getting, so the tangent is perpendicular. Similarly, the region of existence only for r square less than or equal to a, or if you observe, mod of cos theta is less than 1. Value of cos 2 theta or any angle cosine does not exceed 1. So entire curve lies within the circle r is equal to a. If you observe, this curve lies within the circle r is equal to a. So this is circle r is equal to a. So both the loops of the curve lie inside the circle r is equal to a. So this is approximate shape of this particular curve. We are going to learn Rhodes curves today. The tracing of important type of the curve, that is Rhodes curves. So why it is called Rhodes curves? So it is like rose having some petals, some loops, so that's why it is called rose curves. To trace this curve, there are two types of the curves here. R is equal to A sine n theta, R is equal to A cos n theta, where n is an integer. So we go with this number of points that already we have seen in the polar coordinates. Polar curve, this is polar curve, of course. So we go with symmetry and we check the symmetry for these two curves. If as usual there are 3 points there, if theta is equal to minus theta in the equation of curve remains same, then the curve is symmetrical about the line theta is equal to 0. If r is equal to minus r, theta is equal to minus theta in the equation of curve, if we put, then equation remains same, then the curve is symmetrical about the theta is equal to pi by 2 line, that is line passing through pole and perpendicular to the initial line. Similarly, the last one, if r is equal to minus r in the equation of curve, then the equation remains same, any of this, then the curve is symmetrical about the pole r is equal to 0. Now second point, pole and tangents at pole. Now we have to check out whether the curve passes through pole. If we are able to find the value of theta for which r becomes 0, then we say that the curve passes through pole. Now normally both the curve passes through pole, so no need of in fact this particular point. You can, this curve, of course this is positive, it is always passing through pole. To find tangents at pole, we put r is equal to 0 in the equation of curve. So we get tangents like theta is equal to alpha 1, alpha 2 are tangents at pole. Now the important point is maximum value of r is A, lies in the circle, because both sine theta, cos theta, these are periodic functions of period 2 times pi, and naturally the value does not exceeds 1. So r mod of this particular value, it is 1. So r is equal to A is the circle. So entire curve lies within the circle, r is equal to A. Next point, sin theta, cos theta, periodic functions, period 2 pi. So curve does not exist for theta greater than 2 times A, 2 times pi. Similarly, there are some special features of these rose curves. Both r is equal to A sin n theta, r is equal to A cos n theta. If n is even, if n is even, if any number here, n is positive integer, if it is even, then there are 2 n loops formed here, or each of length A. If n is odd, then n loops there in the figure, in the approximate shape of that particular curve. And similarly, there is separate features for r is equal to A sin n theta, which separate observations there. First loop, if it r is equal to A sin n theta, then first loop along theta is equal to pi by 2 by n. If n is even, then as usual draw loops in all divisions from theta is equal to 0 to theta is equal to 2 times pi. If n is odd, then draw the loops in alternate divisions. So in both the cases, here also the same thing it is there, r is equal to A cos n theta, first loop along theta is equal to 0, and here first loop along theta is equal to pi by 2 upon n. If it is cos, then along theta is equal to 0. If it is sine, then it is theta is equal to pi by 2 upon n. Now next, as it is, if n is even, draw the loops in all divisions. If n is odd, then draw the loops in alternate division. Similarly, we prepare table for the values of r and theta over here. We take suitable values of r and theta, and we get the values of r there, and prepare table. From that we'll get the variation of r and theta, how r varies with respect to theta over there. Similarly, we find tan phi, it is r d theta by dr, which is angle between radius vector and the tangent, and this actually gives the direction of the curve tangent at a particular point for the loop. The direction of tangent, whether it is theta is equal to 0 or theta is equal to pi by 2, whether it is perpendicular to theta is equal to 0. So sometimes something you are getting the tangents. And the last point over here, how to find out tangent. It's very clear all the time for any type of the curve. So to find tangent at pole, what we do, this is all the time the same technique it is to be used here. So if I put for the curve r is equal to a sine n theta, if I am taking, and put r is equal to tangents at pole, So put r is equal to 0 in the equation of curve. So I am getting 0 is equal to a sine n theta, or this implies sine n theta is equal to 0, or this implies n theta is equal to 0 pi, 2 pi, 3 pi, for which sine value it is 0, sine angle it is 0, 4 pi, and so on. So theta is equal to 0, pi by n, 2 pi by n, 3 pi by n, 4 pi by n. These are tangents, at pole, for the curve. So this is important observation here to find the tangent. Similarly, if you take the another curve, r is equal to a, second curve r is equal to a, this is general for any r is equal to a cos n theta, or r is equal to a sin n theta. So here also we put r is equal to 0 in the equation of curve. So this implies a cos n theta is equal to 0. So this implies cos n theta is equal to 0, or this is n theta would be, the value is 0 for minus pi by 2 of cos, plus pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on. So it is something like this. Or theta is equal to minus pi upon 2 times n, pi upon 2 times n, 3 pi upon 2 times n, 5 pi upon 2 times n, 7 pi upon 2 times n. So this is the way these are tangents at pole to this particular, n is varying, so any value 2, 3, 4, 5, and so on. So this is the technique of finding tangents at pole to the given curve. Now we trace, and finally we come to the approximate shape of this particular curve. It is Roth's curve. Now we trace one Roth's curve here. Trace the following curves. Trace the curve r is equal to, say here, a cos of 2 times theta. R is equal to a cos of 2 times theta. So n is equal to 2. So it is very interesting to know all the time. N is equal to 2, it is even. So naturally, so the number of points here, number of observation, n is equal to 2, even. So number of loops formed, number of loops of length a, this is equal to 4. It is 2n. 2n means naturally it is 4. Second, now we go for the symmetry. Now if you observe symmetry, for theta is equal to minus theta in the equation of curve remains same. So the curve is symmetrical about, if you cos minus theta is cos theta. So symmetry about naturally as per the procedure, initial line theta is equal to 0. Initial line theta is equal to 0. So this is about symmetry. Third one, now pole for for theta is equal to, if you observe this value, if you put theta is equal to pi by 4 or theta is equal to pi by 4, what happens? See, if theta is equal to pi by 4, then r is equal to a cos of 2 times pi by 4. Means you are getting a cos of pi by 2. Cos pi by 2 is 0. So r becomes 0. R is equal to 0 for this value. Therefore, curve passes through pole. Curve passes through pole, or pole lies on the curve. Curve passes through pole. Curve passes through pole. So this is point number 3. Now to find tangents at pole, to find tangents at pole, put r is equal to 0 in the equation of curve. That is our procedure. Put r is equal to 0 in the equation of curve. So I put r is equal to 0. So I am getting in the original equation cos of 2 times theta, or this implies cos 2 times theta. This is equal to 0 because a is not equal to 0. So naturally to theta, its value is minus pi by 2. Right now I told you plus pi by 2, 3 pi by 2, 5 pi by 2, 5 pi by 2, 7 pi by 2, and so on. So we simplify this further. It is theta is equal to, I take this 2 on the right hand side. So minus pi by 4 plus pi by 4 plus pi by 4, 3 pi by 4, 3 pi by 4, 5 pi by 4, 5 pi by 4, and so on. So 3 pi by 4, 5 pi by 4, 7 pi by 4 are the tangents at pole. Now what we do further, we prepare table for the values of r and theta. That is the next step. Next point, table for the values of r and theta. So this is equation of the curve. R is equal to a cos 2 times theta. Now here if you observe E1 loop, so E1 and first loop, we insert the loop in all divisions. If you observe all divisions, because it is E1 and first loop along theta is equal to 0. That's how it comes. See from the table, for theta is equal to 0. Theta is equal to 0. If you observe from the table, equation of curve, or this it is taken, cos 0 is 1, so r is equal to a. Now theta is equal to pi by 4, say, then r becomes 0. Theta is equal to pi by 2. If you observe, cos pi is minus 1, so it is minus a. Theta is equal to, next value, if you consider here, 3 pi by 4. 3 pi by 4 if you are putting, then it is again 0 there. 3 pi by 0, because cos 3 pi by 4 means, here if you put it 3 pi by 2, you are getting cos 3 pi by 2 is 0. Then cos of next value is say cos pi if you are putting, then cos 2 pi, it is 1, so again a you are getting, then and so on. So this is table for this values. So if you observe the maximum value, maximum value of r is a, and minimum value of r is 0, and minimum value of r is 0. Now if you observe, as here, as theta increases from 0 to pi by 4, r decreases from a to 0. theta increases from pi by 4 to pi by 2, r increases from 0 to a. We take the absolute value. Now, approximate shape of this particular curve is this. Approximate shape for this curve, it is this. Now, if you observe here, so here are the tangents I can draw. So, it is this curve. Theta is equal to 0, theta is equal to pi by 2, theta is equal to pi, theta is equal to 3 pi by 2. So these are the four quadrants. Now I draw the tangent minus pi by 4. So this is tangent. Theta is equal to pi by 4. Theta is equal to minus pi by 4. Theta is equal to minus pi by 4, or it is 3 pi by 4. 3 pi by 4. Then 5 pi by 4 means it is something. Theta is equal to 5 pi by 4 means pi by 4. So if you observe this, now for theta is equal to 0, if you observe, r is equal to a is the first loop here. A for theta is equal to 0, r is equal to a. And as theta increases from 0 to pi by 4, r decreases means, so here is the loop, decreases r, so this is r actually, so decreases from 0 to pi by 4. So here is also this, theta is equal to minus pi by 4. Similarly, pi by 4 to pi by 2, pi by 4 to pi by 2, as theta increases from pi by 4 to pi by 2, r increases from 0 to a. Again, here is the loop formation. So it is of length a, and again theta increases from pi by 2, 3 pi by 4, r decreases from a to 0. Similarly, if you take theta is equal to pi, so here is another loop here. So you are getting this something like this for a. This is a, and again to take some more points here, theta is equal to pi by 4, 5 pi by 4, pi to 5 pi by 4. Here pi, 5 pi by 4. So again it becomes 0 at this particular point. If you observe, r becomes 0 to 5 pi by 4. So it is 0. Again 5 pi by 4 to 7 pi by 4. So this is 5 pi by 4. The next is pi here, pi, 5 pi by 4, and so on. This again becomes a for this value, 3 pi by 2, 0 to 3 pi by 2, and again 3 pi by 2. So this is nothing but 7 pi by 4. So it is something like this you are getting, and this is the loop of length a. If you just check out these values, so you are having this particular form. So this is called four-looped rows, 4 loops there. So sometimes it is called as four-looped rows also. And here is the tangent. If you try to find tan phi, it is something. These are the tangents at this particular point. For r is equal to 0, tan phi is equal to 0. Tan phi, if you try to find out, it is 0 for r is equal to 0. So tangent at theta is equal to 0 is perpendicular to the initial line, theta is equal to 0. If you work out at this particular point, theta is equal to 3 pi by 2, also you are getting tangent is perpendicular to the initial line, theta is equal to 3 pi by 2, and this curve is entirely located because cos theta 2 times theta cannot exceed 1. So mod of r is less than or equal to mod a, means r is equal to a is the maximum value of radius vector. So it is located inside the circle r is equal to a. So this is your four-leaved roads or approximate shape of this particular curve. So this is one tangent. Now if you observe here, so the first loop is along theta is equal to, we put loops in all divisions here if you observe. So there is one loop from pi by 4 to 3 pi by 4, the next loop from 3 pi by 4 to 5 pi by 4, next loop from 5 pi by 4 to 7 pi by 4. It is something like this you are getting. If the curve value of n is even, then we are putting loops in all divisions, and first loop is along theta is equal to 0. So this is the rule actually for first for this if n is even. So this is the tracing of Rhodes curve.